presenting an extension of the framework TypesToSets for Isabelle HOL. The first slide of the presentation is dedicated to an overview of the terms that I used in the title of the presentation. So what is Isabelle? Isabelle is an interactive proof assistant. It is generic in the sense that it supports several object logics, and Isabelle HOL is precisely one of these object logics. As the name suggests, it's based on higher-order logic. However, Isabelle HOL provides several additional features. So what is TypesToSets? TypesToSets is a certain theoretical framework for Isabelle HOL that was conceived by Kunc and Andrei Popescu in 2014. It provides an extension of Isabelle HOL with two new axioms and an efficient algorithm for the relativization of theorems that relies on these axioms. However, TypesToSets offers very little to enable the end users of any proof assistant, including Isabelle, to harness the power of the relativization algorithm that it describes. This is precisely the gap that's meant to be filled by the extension of TypesToSets. The extension of TypesToSets is a software framework for automated applied relativization of definitions and theorems in Isabelle HOL that relies on the theoretical framework TypesToSets. The next several slides will be dedicated to answering the questions: why do we need TypesToSets and why do we need the extension of TypesToSets? So, why TypesToSets? Suppose we would like to formalize elements of general topology in Isabelle HOL. According to the TypesToSets argot, there are two classes of methodologies that could enable us to do this. One is called type-based, the other one is called set-based. The former, the type-based one, is less expressive in the sense that the number of conventional theorems from the area of general topology cannot even be stated, let alone proven in the type-based setting, but the proof procedures work better in the type-based setting, so the proofs are more efficient. The latter methodology, the set-based methodology, is more expressive. So almost every conventional theorem in general topology can be stated and proven in the set-based setting. However, the proofs are far less efficient. Now, the two theorems that are shown on this slide are two different models of the same theorem from the area of general topology. This theorem states that the union of two closed sets is a closed set. The abbreviation CL stands for closed, and the abbreviation TS stands for topological space. The first theorem from the top, this theorem, is a type-based theorem. And the second theorem, this theorem, is a set-based theorem. So why is this theorem called type-based theorem and why is this theorem called set-based theorem? Now, in the type-based setting, the carrier sets or the underlying sets associated with the mathematical structures are modeled as types or collections of all terms of a given type. And in the set-based setting, they are modeled as arbitrary collections of terms of a given type, or sub-collections of all terms of a given type. So, in the first theorem, the type-based theorem, shown here, the underlying set of the topological space is represented by the type variable alpha, shown here. And in the set-based theorem, here, the underlying set is represented by the term variable u, shown here. Which in turn represents an arbitrary collection of terms of the type alpha, shown here. So I hope this explains the differences between the type-based and the set-based results. So in summary, we have two different methodologies for modeling mathematical structures. The type-based and the set-based one. Each methodology has its own advantages and disadvantages. So the users and the developers of the mathematical libraries in Isabelle HOL needed to find a compromise between these two different methodologies. The solution that they converged upon was to provide two sets of libraries of formalized mathematics, type-based and set-based. Unfortunately, before the TypesToSets proposal, Isabelle HOL did not offer any tools for performing the conversion of the type-based theorems to the set-based theorems or the set-based theorems to the type-based theorems. So the aforementioned solution resulted in what I would call the duplication of proof efforts on a dramatic scale. Almost every theorem was stated and proven twice, independently, once in the type-based library and once in the set-based library. This is exactly the problem that the framework TypesToSets is meant to address. The relativization algorithm associated with the framework TypesToSets enables efficient automated conversion of the type-based theorems to the set-based theorems. So for example, it can convert this theorem, the type-based theorem shown here, to this theorem shown here. This is indicated by the arrow shown here with the annotation array. where array stands for the relativization algorithm. So I believe that the only question that remains to be answered is why do we prefer to convert type-based theorems to the set-based theorems and not the set-based theorems to the type-based theorems? The primary reason is efficiency. It was already mentioned that the proof procedures work better in the type-based setting. So it makes little sense to design inefficient and verbose set-based libraries first and then convert them to concise and efficient type-based libraries. So I hope that I was able to convince you that the framework TypesToSets can be very useful. Now what remains is to convince you that the extension of TypesToSets can also be very useful. So let's move on to the next slide. Why the extension of TypesToSets? I have identified several reasons. One of these reasons is automation and convenience. Now the code listing on the left-hand side here shows what it takes to apply the relativization algorithm to the type-based theorem using the original interface of TypesToSets. The problem with the original interface and the associated methodology is that they require the users to have a deep understanding of the relativization algorithm and its various dependencies, of which there are many. Now, here's all it takes to apply the relativization algorithm using the extension of TypesToSets. The code is concise, and almost no knowledge about the relativization algorithm is required on behalf of the users. Unfortunately, the result of the application of the raw relativization algorithm can contain some redundancies. However, the extension of TypesToSets provides tools for post-processing of the raw result of the relativization. Now, this code listing here shows a more usual use case for the extension of TypesToSets. While the code is slightly more verbose, all the keywords here, apart from the keyword TTS here, are used only for post-processing of the result of the application of the relativization algorithm. Now, I hope that this provides some motivation, but there are certainly more. Unfortunately, as you can see, the result of the application of the relativization algorithm does not appear in the code listings in a human-readable format. In itself, this could already be seen as a major limitation of any interface. However, the problem is even worse than it appears. As a consequence, this creates a problem with backward compatibility. Fortunately, the extension of TypesToSets provides a solution to this problem: code generation. So, let us take a closer look at what happens in the video. Now, here's a list of type-based theorems, and here's one of them. Now, the command TTS lemma that applies the relativization algorithm to the type-based theorems includes a tool for code generation. Here it is. The tool generates the statements and the proofs of the set-based theorems that correspond to the type-based theorems provided as inputs to the command. And all it takes is a click of a button to generate the code. Now, I hope that this tool provides another reason for preferring the extension of TypesToSets. But there are certainly more. Right. So I'm afraid that all code listings shown on the slide hide the requisite setup that was required before the relativization algorithm could be applied. Such a setup is required for every constant that appears in the type-based theorem, but the setup is reusable for any theorem that uses any of these constants. As part of our work on the extension of TypesToSets, we have designed two auxiliary software frameworks that can automate the requisite setup for the application of the relativization algorithm: an overload definition, abbreviated as UD, and conditional transfer rule, abbreviated as CTR. The diagram shown on the slide provides a setup for the constant CL, or close, that you might remember from the first example, using UD and CTR. Unfortunately, I will not have enough time to explain the details of the implementation or the functionality of either the UD or CTR, and have to refer you to the proceedings article if you're interested in finding out more details about these frameworks. However, I hope that it is apparent to see that both UD and CTR provide another reason for preferring the extension of TypesToSets. Now, I hope that by now I was able to convince you that the extension of TypesToSets is at least almost as useful as the framework TypesToSets itself. In the remainder of the presentation, I will try to explain the functionality of TypesToSets and the extension of TypesToSets in more detail, and provide several application examples. The framework TypesToSets introduces two new axioms: local typedef rule and an overloading rule, and the relativization algorithm that uses these axioms. The consistency of Isabelle HOL augmented with these axioms was shown in one of the articles by Andrei Kunc and Andrei Popescu. The relativization algorithm associated with TypesToSets converts the type-based theorems to the set-based theorems while using the unoverloading rule in step 2 and the local typedef rule in step 6. More details about these axioms and the algorithm can be found in the original articles by Ondr, Kunc, and Andrei Popescu. However, these details are largely unimportant from the perspective of the extension of TypesToSets. So let us continue to the description of the extension of TypesToSets. As I mentioned before, the extension of TypesToSets is a software framework for Isabelle. The primary functionality of the extension of TypesToSets is available via the commands TTS_context, TTS_lemmas, and TTS_lemma. You've already seen all of these commands in action before. The only concept that appears on the slide that hasn't been mentioned before explicitly is the extended relativization algorithm, abbreviated as ERA. As the name suggests, it is the relativization algorithm with several amendments. But for now, let us return to the commands. The command TTS_context is used for the parameterization of the ERA. The commands TTS_lemmas and TTS_lemma can both be used for the application of the ERA. However, the command TTS_lemmas is also meant to be used for code generation, and the command TTS_lemma is also meant to be used for the presentation of the relativized results in a human-readable format. Now let us return to the ERA. The example shown on this slide presents the relativization of a theorem from the area of general topology. You've already seen this theorem before, however it is stated in a slightly different format using Isabelle schematic variables. For our purposes, these variables, denoted using the question marks, may be viewed as variables universally quantified at the top level. Now, the ERA consists of three parts: initialization of the relativization context, kernel of the ERA, and post-processing. The initialization of the relativization context is an implementation-specific detail that is hidden from the view of the end users of the interface associated with the extension of TypesToSets. It provides the necessary definitions and theorems for the execution of the next step of the ERA, called kernel of the ERA. Now, the kernel of the ERA is similar to the original relativization algorithm of TypesToSets. It does provide certain additional functionality and implementation-specific details, and they are described in detail in the proceedings article, but I feel it's best to omit them during the presentation. Now, it can be seen that the output of the kernel of the ERA contains several redundant assumptions that are then eliminated in the final stage of the ERA, the post-processing. So the purpose of the post-processing is to format the theorem for readability and convenient rule application. Now, I am coming to the end of the description of the extension of TypesToSets. I hope that you found the summary given here useful, but as I mentioned, many details have been omitted for brevity and are only available in the proceedings article. But let us move on to the next section of the presentation, application examples. Since the first official release of the framework TypesToSets, there has been a growing interest in the use of TypesToSets for applied relativization. Here are some of the examples of published articles that use TypesToSets in some capacity. Perhaps the most significant application example of TypesToSets was developed by Fabian, Immler, and Bohua, Zhan as part of their work on the article Smooth Manifolds and Types for Linear Algebra in Isabelle HOL. They performed the relativization of over 200 type-based theorems in the area of linear algebra from the standard library of Isabelle HOL using TypesToSets. As part of our work, we have also developed several application examples using the extension of TypesToSets. For example, the library TypesToSets vector spaces is a remake of the applied relativization work done by Fabian, Immler, and Bohua, Zhan using the extension of TypesToSets. We have also developed two additional libraries of relativized results. They are described on this slide, but we will leave them without further elaboration. So let us take a closer look at a more specific example of relativization of a type-based theorem performed in the library TypesToSets vector spaces. The proof of the type-based theorem, shown here from the standard library, consists of nearly 100 lines of code. Having an appropriate parameterization in place, here is all it takes to perform the relativization of this theorem using the extension of TypesToSets. The invocation of the command TTS_lemmas also generates the following code, which presents the relativized theorem in a human-readable format. I hope that this example once again shows the power of the extension of TypesToSets, but I'm afraid we're coming to the end of this presentation. So, in summary, we have designed a software framework extension of TypesToSets for the application of the relativization algorithm associated with the original framework TypesToSets. Thus, we have largely solved one of the problems that was posed in the original article on TypesToSets by Andrei Kunc and Andrei Popescu. And finally, we provide some ideas for potential future research directions, which include the integration of the functionality of the extension of TypesToSets with the standard Isabelle commands, and the mechanized verification of the consistency of Isabelle HOL augmented with the local typedef rule and the unoverloading rule. And we now come to the final slide, which is dedicated to acknowledgements. I hope that you found the presentation useful, and I will be happy to answer your questions.
Thank you. All right. Oh, looks like there's already one question in the Q&A chat. Can you give some examples of point set topology that cannot be formalized in the types approach?
Yes, of course. Basically, any theorem that anything about subspaces. Well, I wouldn't say cannot be formalized. I'd say that it can be formalized with difficulty and with some amendments to the usual approach, to the kind of canonical set theoretic approach. Basically, the problem is that any kind of, well, subalgebra or subspace topology needs canonical set theoretic subset relation, which in Isabelle Hall's types theory just doesn't exist. So it's basically a syntactic limitation that prevents us from doing this. It's actually described in the paper. So,
thank you. Any question? Oh, yes, we have one locally.
Thank you. Can the technique be applied to, does it have implications more generally to, relativizing other types of proofs that, different formats? I mean, one of the big problems that I often come across is, different formalizations of real numbers, for example, and trying to translate proofs, there's one library uses one formalization, one library uses another. Can the same techniques be used, or?
Right. I'm not sure if I heard the question correctly, but I will. There were some interruptions, but I will try to answer based on what I've heard. Yes, if I understand your question correctly, then certainly it can be. Basically, I only presented the topology example as one of many, many examples. As I mentioned before, that basically it can be applied to vector. Well, it's already been applied to vector spaces, and basically. Probably just about any area of mathematics. Yes, it's so. I'm not. Does that answer your question, or did I not hear it correctly?
Yes, thank you.
Okay, right.
Great. Any other questions here locally? Let me check online. Looks like maybe not. I guess one question that I had during your talk was part of the motivation was this duplication between the two worlds, right? The type-based and the set-based approach. After having implemented this, do you have a sense of how much it improves that situation?
Well, it depends on what you mean by the improvement. Certainly, it reduces the duplication of proof efforts. So obviously, we don't need to prove the same theorems over, well, semantically the same theorems over and over again. So in that sense, certainly, yes, it has improved the situation quite dramatically, I would say. Or again, does that answer your question?
Yeah, I think that's. I guess I'm not familiar with how Isabelle Hall is set up for that. So in terms of duplicating code, anytime you can avoid it, it seems like a good thing. So it sounds like you now can basically auto-generate all of the set-based proofs from the type ones.
Well, all of the ones that you can formalize in a type-based setting. Usually, what would normally, I think, happen is that you would first create a type-based library, and then you would convert the type-based library to the set-based library, and then you would add additional results that can only be conveniently formalized in the set-based setting. So that's how it normally would work.
Right. Any other questions? Oh, there's one more online. Related to the previous two questions, have you considered deploying your tool in a systematic manner to the existing Isabelle Hall theories? How would you estimate the effort to do that?
Well, certainly, as I mentioned before, I have already converted, well, first of all, Fabian, Immler, and Bohua, Zhan converted the vector spaces part of the standard library to the set-based setting using the TypesToSets approach. And then I recreated, so I basically recreated their efforts using the extension of TypesToSets. And I have also formalized, I already mentioned, I formalized, well, I also took about 800 theorems from the standard library, from the areas of general topology, abstract algebra, order theory, converted them to the kind of set-based setting using the type-based approach. It certainly has been considered. The effort, well, obviously it will be substantially reduced in comparison to what it would take to do it using the kind of raw TypesToSets approach. So the one that was used by Fabian and Bohua in their work. But I can't really estimate it. I don't really know how many theorems in, say, in the archival formal proofs are type-based and how many are really set-based. So it would need to be considered very carefully. So I can't really answer this question directly. It would certainly be much less than what it would take to formalize everything using essentially from scratch by proving set-based theorems directly. So that's something that we can have no doubt about.
Thanks. One more question that I had, maybe I just missed it during your talk. It wasn't completely clear to me whether the translation is complete for everything that's in the types world, or if your tool can't handle some for some reason.
Oh, yes. I'm afraid it certainly has some limitations. So these limitations are mostly related to one of the SAT packages on what it relies. It relies on the so-called framework transfer available in Isabelle, and framework transfer has certain limitations. In general, it's basically, it has to do with the kind of side conditions of transfer that needed to transfer theorems from, say, that need to set up so-called transfer rules. So they can be quite involved, and they basically, that's the part that hasn't been fully standardized yet. So yes, but quite often these complications can be avoided, or we can find ways around that. Actually, Fabian Immler and Bohua paper describes some of these complications and what they had to do to avoid them in quite a nice manner. So it's usually possible to do something, and it requires a little bit of extra effort. But yes, it's not a universally applicable tool, so it certainly has some limitations.
But still useful nevertheless. Thanks.
Yes.
Any other final questions, comments? It looks not. So let's thank the speaker again.